Our view of the stars is limited. What we see in the vastness of the universe is not the big picture, but only a section determined by several natural factors. But what is hidden in the part of the universe that we cannot see? Is there a way to solve this mystery? Well, there is, and the growing evidence suggests that there's something bigger out there that's reaching out into our world. And the Earth is the center of the universe. But before we think we've lost our minds to the Middle Ages, let's briefly explain what this means. The geocentric view of the world, which places everyone at the center of space, has long been obsolete. Nevertheless, our blue home planet is still the center of the observable universe. Because, as mentioned at the beginning, our view of deep space is glowing. The universe is isotropic, that is, a background that always looks the same to an observer, regardless of the observer's orientation. The radius of the observable universe is in turn determined by how far light has traveled to us since the Big Bang. According to the standard cosmological model, the universe was born about 13.8 billion years ago, and the optical barrier can be assumed to be 13.8 billion light-years from us. But this is not true. At this point, we must remember that the universe is constantly expanding, and as a result, the distances it travels are constantly expanding. In simple terms, this means that the viewing horizon is 46 instead of 13.8. 3 billion light-years. The most distant objects we can observe today are 40 million light-years from Earth. As a result, the study of these boundary structures is always optically backward. Since the light emitted from it cannot reach us now, it is impossible to know about the current processes at this distance. Against this background, the question of what exists outside the observable universe is doomed from the start. However, despite all the observational horizons and natural barriers to vision, there are some experts who have cracked this puzzle. As a result, a few years ago, researchers realized a strange phenomenon that contradicts our current assumptions and leads us directly into the deepest secrets of the invisible space. Is there a space giant hiding there? Basically, according to the general assumptions of cosmology, the proper motions of galaxy clusters with respect to the background radiation should be randomly distributed in all directions. And again, for a brief classification, the background rays, or more precisely, the cosmic microwave background rays, represent a relic of the immediate aftermath of the Big Bang that still fills the universe today. Between 2001 and 2010, NASA's Wilkinson Microwave Anisotropic Probe, or WMAP for short, was again dedicated to investigating disturbances in the cosmic background radiation. And the NASA Task Force, in 2008, led by Alexander Kashlinsky, while analyzing the WMAP data, they noticed a strange pattern that shouldn't be there. Scientists did not detect the movement of galaxy clusters scattered in all directions, but a surprisingly uniform flow. This is not the case. In all cases, the galactic flow rate increased with increasing size. The bottom line is that such a phenomenon can only occur due to extreme gravity. But what structure might be responsible? Well, unfortunately, this question is not entirely reliable. All studied galaxy clusters are moving towards a point outside the observable universe. Henceforth known as the dark stream, the galaxy caravan was re-examined in 2010, which increased the number of galaxy clusters floating in the dark stream from 700 to 1,400. Although there were some differences in the direction of movement in the 4 observed segments, all areas showed a clear correspondence. Since then, astronomers have gathered further evidence of extreme gravity and tantalizing mystery beyond the observable universe. According to Alexander Kashlinsky, for some time the matter in the observable universe cannot explain the measured galactic flow. We don't know in the same breath what is responsible for it. In this regard, A NASA astronomer from the Goddard Space Flight Center is quoted as saying that the dark stream theory has been criticized. So our cosmic field of view hides an accumulation of energy and matter exceeding certain orders of magnitude? Or we do? G here with strange periodic distortion effects from neighboring universes? Critics of the dark current theory are critical of these questions, and for the simple reason that the leading researchers have raised eyebrows. G errors. In this sense, the previous study concluded that it is not a physical flow, because the basic anisotropy, or in other words, the directional dependence of the cosmic background radiation, was neglected in the previous study. Furthermore, the study of more than 550 supernovae also did not reveal an impossible pattern of synchronous motion, but rather a pattern that fits easily into our cosmological models. Then there's the data from ESA's Planck satellite, which has yet to provide any further evidence of a mysterious black stream. So, can we finally save the hidden superstructure theory? Koszaliński emphasized that the observations were based on data from more than 1,000 billion galaxy clusters that were measured up to 3 billion light-years away. Statistical coincidence can therefore be ruled out, and it is clear that dark currents have not yet been definitively confirmed. The question is, what is behind it? And whatever this may be, if there really is a dark stream generator, it also means that there must be something behind our observable universe. And of course, Koszaliński's researchers are not the first, nor the only ones, to deal with the question of what might be behind this horror. Needless to say, at this point, dealing with this topic is always pure speculation, but the relevant theories are surprisingly varied. And even if this first hypothesis sounds a bit strange at first, he says, in effect, that the invisible universe is structured in the same way as the observable universe. However, if we move this scenario to infinite space, things get even more fascinating, because eventually we will find different things. And by that, we really mean different things. In this context, there is another solar system, complete with Earth, that is similar to ours in every way, except this one. Maybe you had cornflakes instead of toast this morning. In another solar system, you skipped breakfast altogether. In another, you got up this morning to rob a bank. Some experts even believe that there is an observable universe that is exactly like ours. In other words, there is a version of you in infinite space that accurately reflects everything you do. At first glance, this thought may seem beyond the limits of our imaginations, but infinity also offers endless possibilities. Alternatively, we could be on one of an infinite number of space shuttles. According to Koszaliński's alternative universe theory, most of the universe is expanding in a perpetual inflationary fashion, a process that stops at most formless subcontinents. Individual sub-universes may contain their own natural fixed values and then individual physical laws. Multivariate theory follows a similar line. According to the motto, there is a whole world that can be imagined. We only exist because the laws of physics are so perfected that there must be a world among countless universes where life can flourish. In detail, the ideas of string theory are now applied to membranes. Broken, the whole point of the whole thing is that these membranes in the 11th dimension embody completely different universes, and when they collide, they create a new universe. One of the strangest aspects of this theory is the idea that all the gravity we experience in our universe enters our world in a different dimension from another universe. Ultimately, however, this theory may explain why gravity is so weak compared to the other fundamental forces of physics. If you want the next video to appear on your homepage, you can now concentrate your efforts and hit the subscribe button. Be part of our community and never miss an exciting video from us. See you soon. We humans crave knowledge. The ability to understand the structure and function of our environment has helped our species reach a highly evolved point in its history. Although humanity regularly produces new technological breakthroughs, there are countless realities that almost completely elude our knowledge. Although these mysteries of life raise great question marks among experts on the one hand, the fascination generated by these unsolved mysteries is equally undeniable. This topic becomes especially exciting when it seems beyond our horizons. In the case of the universe, despite all the rockets launched into orbit and the successful moon landing in 1969, research is still in its infancy. At present, we know only a small part of what is hidden from our view in the infinite space. Space. Just how big the universe is in general is a mystery that has plagued humanity for countless centuries. In today's installment, we present the current state of research on this topic. We will show you the current state of astronomical knowledge and discuss why the question of the size of the universe is so difficult to find. If you like our videos, please support us with a thumbs up, subscribe to Simple Space, and look forward to future videos. Let's begin our journey through the vastness of the universe, what we can see about the universe. When we look up at the night sky full of amazing stars, most of us realize that we are small in relation to the big picture. The thousands of twinkling stars in the firmament silently bear witness to the fact that our tiny home planet is only a small part of what we call the universe. However, a quick glance at the sky is enough to realize that the universe must be bigger than we imagine. But can we scientifically understand the magnitude of the universe in detail? This question has always been a central point in the field of cosmological research. Even this question can never be satisfactorily answered. However, this does not necessarily mean that experts will not try to answer it. We now know that the universe was created about 13.8 billion years ago. The process known as the Big Bang describes the formation of matter, space, and time, and is therefore considered the birth of our universe. In physical cosmology, the cosmic microwave background rays play a key role in studying the earliest state of the universe. It is a type of radiation in the microwave range that was created during the Big Bang and flows through the vastness of the galaxy today. By looking at said radiation and measuring it at different distances, researchers were able to determine the approximate age of our universe. At the same time, this also means that we can now look at 13. Space is 8 billion light-years from Earth. If one wants to visualize this situation, one can draw a spherical image with the Earth as the center. The remaining spheres now represent the sphere we can see from our blue home planet. In technical terms, the universe visible to us is called the event horizon. In detail, the event horizon describes the spectrum of objects whose reflected light is visible only from Earth. However, the processes behind this event horizon are currently completely invisible to our human eyes. We don't know exactly what lies behind the observable universe, so the question of the total size of the universe is more difficult to answer. The expansion of the universe. If one accepts the question of the completeness of the universe, an important fact cannot be overlooked. As scientists know today, the universe is always expanding. One object was still around 13 at the time of the Big Bang. 8 billion light-years from Earth, the distance between the celestial body and our planet is now 46 billion light-years due to the expansion of space. This situation also means that in the future, we may see things in the firm that are still hidden from our eyes. At the same time, due to the expansion of the universe, some celestial bodies will disappear from our star charts in the future. Naturally, during these observations, we put the Earth at the center. This is due to spatial conditions, since there is no other way than to define our planet as the central vantage point in the star chart. But at what geographic point our blue home planet is located within the ever-expanding universe is impossible to answer today. Measuring the universe. As we mentioned earlier, an international team of experts is trying to explore all the dimensions of space despite all the difficulties. To do this, experts use several different methods that help researchers study the vast dimensions of the universe. Key research methods include some measurements of early cosmic radiation. Using these radiation movements, scientists can determine different distances and try to calculate the dimensions of the universe. The oldest light source that researchers have been able to detect is 92 billion light-years from Earth. Conversely, however, this does not mean that the object located is an external component of the universe. The question of whether the universe ends is much more difficult to answer than most of us think. Basically, the farther an object is from our planet, the longer it takes for the light it reflects to reach us. Some objects in galaxies are so far away that the light they emit sometimes takes billions of years before we see them from Earth. Therefore, there are countless rays of light in the universe right now that have been traveling through the universe for billions of years, but have yet to reach us. The question of the shape of the universe. To calculate the size of an object, it is necessary to know the corresponding shape of the object. The shape of our universe is still an unsolved question in research that has not been satisfactorily answered. Although some scientists suspect that our universe is built like a self-contained sphere, which may contain other media, other experts believe that the universe is a flat space that is also infinite. If the first thesis were followed, our universe would be a finite self-organizing structure somewhere. So, if our galaxy is indeed a finite construct, at least theoretically, it would be possible for scientists to mathematically determine the dimensions of the universe if they had the right information. However, if our universe is infinite, then the question of size cannot be answered. By definition, infinite objects cannot be assigned any size because they have no mathematically interpretable boundaries. According to NASA, the universe is an infinitely large, flat structure. However, our universe has an infinite age and, as mentioned earlier, was created about 13.8 billion years ago. So we can check the time interval between the Big Bang and today. Unanswered question? Although the international team of experts does not currently know how big the universe is, researchers can say with confidence that the universe is an incredibly large, even infinite structure that exceeds the dimensions of our horizons. The precise study of the universe is a work that will engage countless generations of experts. Although we may never know the vast details of the universe in our lifetimes, this will not diminish our interest in the fascinating world of alien stars and planets. What do you think about the true size of the universe? Do you think the universe is a closed entity or an infinite structure? Feel free to let us know your thoughts on this topic in the comments. Thank you very much, and see you next time. If you follow our channel or astronomy developments regularly, you probably know that the new James Webb Space Telescope is completely revolutionizing the way we look at the universe. Last September, NASA released another image of the new super telescope, quite a lot of noise. The image shows the icy planet Neptune, and it's the best we've seen of this fascinating planet in 30 years. In fact, Neptune is one of the least studied and most mysterious planets in the solar system. Before moving on to the blue ice giant, we invite you to subscribe to our channel if you haven't already done so, and activate the notification bell so you are guaranteed not to miss any of us. Future videos. Also, if you enjoyed the latest discoveries about Neptune, give us a like at the end of the video. Now we start with a few facts about the blue planet at the end of the solar system. Neptune facts. Neptune is the 8th known planet in the solar system, and since Pluto was stripped of planet status in 2006, the latter is measured by diameter, making Neptune the 4th largest, 3rd most massive and densest planet. In the solar system, It has about 17 times the mass of Earth and is slightly more massive than its identical twin, Uranus. Neptune is composed mainly of gases, liquids, and ice. Officially, it's an ice giant. One orbit around the Sun requires Neptune to be at a distance of 8 billion miles, 164.8 Earth years. Neptune was the first planet discovered using only mathematical calculations. Galileo Galilei saw a blue sky in the 17th century, but he mistook Neptune for a star. It wasn't until 1846 that British mathematician and astronomer John Couch Adams discovered through mathematical calculations that there must be another planet behind Uranus. Discovered in 1781, Couch's calculations were confirmed simultaneously by the French astronomer Urbain Le Verrier. The planet was first seen on September 23, 1846, by a German astronomer named Johann Gottfried Halle. Looking at the night sky from the Berlin Observatory, he named Neptune the 8th planet in the solar system. Trademark of Neptune its blue color. This is due to the peculiar vibrational pattern of the molecular structure in methane gas, which makes up the bulk of Neptune's structure. The blue color also gave the planet its name as the god of the sea. Neptune is one of the least studied planets to date. Observations of the planet's atmosphere over the past few decades have shown sometimes dramatic changes in the ice giant's structure. This caused great concern among scientists. Because so little is known about Neptune, researchers don't know what to do with these observations. Image of Neptune by James Webb. The first exciting images of Neptune were provided by the Voyager spacecraft in 1989. A probe launched in 1977 reached the planet after a 12-year flight. Neptune, however, was not Voyager's target. Voyager's binary probe is designed to fly through the entire solar system and then enter interstellar space. This image was to remain the best for humanity on Neptune for over 30 years. The first Hubble Space Telescope also provided images of the ice giant, but the quality was mediocre. Scientists are even more excited about the launch of the new James Webb Telescope. In September 2022, we saw Neptune in a completely new light. Webb not only captured the clearest view of this distant planet's rings in more than 30 years, but his cameras also show the ice giant in a whole new light. Image captured by NIRCam, infrared camera, in the infrared range of 0.6 to 5 microns. In this way, Neptune does not appear blue, but is very dark. The dark spots are probably methane gas that absorbs red and infrared light. Bright lines and spots, on the other hand, methane ice clouds. They are almost white due to the reflection of sunlight. With this technique, Neptune's fine ring system was clearly visible for the first time. These rings have been known to scientists for a long time, but prior technology could not visualize or image the rings. Made of ice crystals, a thin, bright line circling the planet's equator indicates atmospheric circulation. Simply put, these are the strong winds and storms on Neptune's surface. A previously known vortex at the South Pole is clearly visible in James Webb's image. Also, the first is a depiction of a continuous cloud band covering the planet at high latitudes. Light filtering techniques allow scientists on Earth to determine the precise composition of gases and other structures. Study the rings alone. First observed by Voyager 2 in 1989, it will provide exciting new information about the ice giant at the end of the solar system. For astronomers, this is a milestone in the study of Neptune, and a long-awaited relief for NASA's current lack of funding for its own Neptune exploration. Big dark spot Neptune's surface processes are among the last great mysteries of the star system. In 1989, Voyager 2 discovered the Great Black Spot during a flyby of Neptune's southern hemisphere. It is a giant storm similar to Jupiter's Great Red Spot. In 1994, using the Hubble Space Telescope, a team of researchers took a closer look at the Great Dark Spot. The researcher was surprised that a high-pressure area the size of Eurasia suddenly disappeared. Instead, scientists discovered a new dark spot in the northern hemisphere. Its disappearance a few years later suggests that the large storms that dominate Neptune's surface are shorter-lived than Jupiter's. On its surface, a storm called the Great Red Spot has persisted for centuries and in the same place. Neptune's storms may be shorter than those of its older brother Jupiter, but when it comes to wind speeds, Neptune is the undisputed king in the system. Its gusts reach 1,305 miles per hour. In comparison, the strongest tropical cyclone reaches 186 miles per hour. So you really don't want to face a Neptune storm. Mysterious processes on Neptune's surface. In 2020, scientists are thrown into chaos. A team of researchers from the University of California, Berkeley, using the Hubble Space Telescope, observed a storm that was wider than the Atlantic Ocean. The storm originated in the northern hemisphere of the planet. Since its opening in 2018, Berkeley experts have looked at what's going on every year. In 2019, the storm began to turn south. Moving toward Neptune's equator is where storms typically occur. But to scientists' surprise, Hubble found that in August 2020, the vortex had changed direction and was heading north. Although Hubble had been observing similar black spots for nearly 30 years, this atmospheric behavior was completely new. Researchers don't know what these movements mean, or whether the events are rare or worrisome anomalies. The largest hurricane ever seen at Neptune was 4,600 miles in diameter. Researchers have been tracking the storm's behavior since 1993, and they have seen the storm disappear several times, perhaps dissipating and appearing not far from where it disappeared. Scientists would like to know more about these events. The theory says that the storms only disappear from the surface, but continue to rage in the deep layers of Neptune. From time to time, events could be seen again on Earth. We still don't know what happens in the deep layers of Neptune. NASA was supposed to send a probe to the blue planet. Like Cassini, it can be brought down to the planet after its mission is over. During a flyby through Neptune's layers, researchers could finally get it information they missed. It's still a pie-in-the-sky idea, but there's no doubt that Neptune will get its own investigation at some point. Perhaps NASA will combine a mission to Neptune with a search for the mysterious Planet X, whose orbit is said to be behind Neptune. Since Pluto is no longer a planet, Neptune is the eighth and last of the main planets in the system. However, orbital calculations of some objects in the solar system indicate that there must be another large planet behind Neptune. Planet 9, or Planet X, orbits the Sun in a very eccentric orbit that is not even visible due to poor light conditions. If Planet X is in orbit, its orbital period around the Sun could be as long as 1,000 years. Theoretically, this planet will be visible with modern telescopes every few hundred years. Neptune's largest moon, Triton. We conclude with another look at James Webb's new image. Surely, when you saw the photo, you immediately wondered what the blue-green fire in the background of Neptune is. Well, even though this scene looks like a bright shining star, the mysterious green glow is just the moon. This image shows 7 of the 14 Neptune moons known so far, and the one that shines so brightly is Triton. Triton is the largest of Neptune's moons and the size of Earth's moon. Because it orbits the moon in a highly elliptical orbit, researchers speculate that Triton may have once been a Kuiper Belt object that was pulled by Neptune's gravity. The moon appears green in this image due to special filtering of the image. As an icy moon, Triton also rarely reflects sunlight well. Triton, Jupiter's moon Europa, and Saturn's moon Enceladus have similar ice volcanism. There may even be a liquid ocean beneath the moon's icy crust. So the Neptune zone would have a lot to learn about this part of the solar system. Until then, we're curious to see what new observations the James Webb Telescope will surprise us with. Apparently, researchers are now looking at Neptune regularly with the new telescope. If there are new interesting discoveries, you will definitely know here. Finally, leave us a comment and think about the latest discoveries around Neptune and the interesting image from the James Webb Telescope. We'd love for you to join us today and watch. Next time in Plain Space. Albert Einstein's theory of relativity, comprising both the 1905 special theory of relativity and the 1915 general theory of relativity, revolutionized our understanding of space-time and the very structure of the universe. The special theory of relativity introduced the revolutionary concept that time and space are not absolute, but relative and intertwined into a single four-dimensional continuum known as space-time. Before Einstein, Isaac Newton's system of absolute time and space reigned supreme. However, Einstein's equations showed that the measurements of time and space depend on the velocity of the observer relative to the object being observed. It has led to such mind-boggling consequences as time dilation, where moving clocks go slower than stationary ones, and length contraction, where objects shrink in the direction of motion as their speed approaches the speed of light. Einstein's general theory of relativity expanded these ideas to include gravity, which was reinterpreted not as a force acting at a distance, as Newton had described, but as the curvature of space-time under the action of mass and energy. Massive objects, such as stars and planets, create warps in the fabric of space-time, and these warps dictate the motion of objects and the passage of time. This concept was clearly confirmed during the solar eclipse of 1919, when observations showed that light from distant stars swirled around the Sun exactly as Einstein's equations predicted. The implications of the general theory of relativity were profound and far-reaching. It has allowed us to understand phenomena such as black holes, whose enormous gravitational fields bend space-time to the point where even light cannot escape. It also predicted gravitational waves, ripples in space-time caused by accelerating masses that were directly detected a century later in 2015 by the LIGO experiment. In addition, the general theory of relativity is essential to understanding the cosmic expansion and curvature of the universe, laying the foundation for modern cosmology. Einstein's theory revolutionized not only our conceptual framework, but also our practical understanding, influencing everything from GPS technology to the deepest questions about the origin and fate of the universe. Time dilation, a key concept derived from Einstein's theory of relativity, has profound practical implications for space travel. This phenomenon arises from the interaction of velocity and gravitational fields, leading to scenarios in which time can run at different speeds for observers in different states of motion or gravitational influence. In the context of space travel, especially at speeds approaching the speed of light, time dilation can create pronounced differences between the experiences of astronauts and those who remain on Earth. One important implication is the possibility that prolonged space travel could lead to age discrepancies between astronauts and people on Earth. For example, if astronauts traveled at close to the speed of light, they could return from a trip having aged only a few years, while on Earth decades or even centuries might have passed. This effect, known as Ndamp, quote, the Twin-Ndamp, quote, paradox, is not just theoretical. It has practical implications for planning future interstellar missions, affecting both the logistics and psychological aspects of deep space exploration. In addition to its theoretical implications, time dilation also affects current space travel technology. For example, accurate clock synchronization is critical to the operation of the Global Positioning System, GPS. Satellites in orbit experience both gravitational time dilation and velocity-related time dilation, causing their onboard atomic clocks to run at a slightly different rate than those on Earth. Engineers must take these differences into account to ensure the accuracy of position calculations and the day-to-day application of time dilation principles. In addition, understanding time dilation helps in developing strategies for human exploration of distant celestial bodies. Missions to planets such as Mars, which require significant flight times and exposure to various gravitational fields, require careful communication planning and coordination to account for relativistic effects of velocity and gravity. In the prospect of potential journeys to other star systems, relativistic effects become even more important, requiring advanced propulsion technologies and innovative solutions to take advantage of time dilation and mitigate its challenges. Time dilation is not just a fascinating theoretical idea, but a fundamental aspect of practical space travel that affects how we plan, execute, and conceptualize humanity's spacewalks. Gravitational waves, ripples in the fabric of space-time predicted by Einstein's general theory of relativity, have opened an unprecedented window into space. These waves are generated by some of the most violent events in the universe, such as colliding black holes, merging neutron stars, or even the remnants of the Big Bang itself. When these massive objects accelerate, they distort space-time by sending out ripples that propagate at the speed of light. The detection of these waves provides insight into the structure of the universe and the fundamental forces at work in it. A major way in which gravitational waves deepen our understanding is their ability to convey information about cosmic events that are otherwise difficult or impossible to study. For example, when LIGO, the Laser Interferometer Gravitational Wave Observatory, made the first direct detection of gravitational waves in 2015, it observed the merger of two black holes. This event not only confirmed the existence of gravitational waves, but also provided the first direct evidence for the existence of binary black holes. Such mergers emit gravitational waves that carry unique signatures that allow scientists to determine the mass, distance, and rotation of the black holes involved in the merger. With continued observations, we can build a detailed catalog of black hole collisions, which will help us better understand their formation and evolution. Moreover, gravitational waves allow us to understand the extreme conditions and physics that occur when neutron stars merge. These cataclysmic events can produce kilowaves, emitting heavy elements such as gold and platinum, and allowing the study of nuclear physics under the most extreme conditions. The detection of gravitational waves from such events, combined with electromagnetic observations, creates a multi-messenger approach to astrophysics that provides a complete picture that can reveal the composition, structure, and behavior of neutron stars. Gravitational waves can also be used to study the early universe. Soon after the Big Bang, violent processes must have generated primordial gravitational waves, giving a direct indication of the infancy of the universe. If discovered, these primordial waves could provide empirical evidence for inflationary periods and fundamental particles, further illuminating the conditions that shaped the cosmos at its very beginning. Gravitational waves are a revolutionary tool in our quest to understand the universe. By allowing us to observe and analyze cosmic phenomena that would otherwise be hidden or opaque, they expand our knowledge of the structure, origin, and fundamental laws governing the cosmos. This emerging field promises to answer some of the deepest questions in astronomy and cosmology, combining observations with theory in new and enlightening ways. Wormholes, also known as Einstein-Rosen bridges, are theoretical passageways in space-time that can create shortcuts between distant regions of the universe. This concept emerged from Einstein's solution to the field equations in the general theory of relativity. Imagine space-time as a two-dimensional sheet. A wormhole is like folding a piece of paper so that two distant points touch each other, creating a straight path between them. The idea is appealing because it suggests the possibility of traveling at speeds faster than light, traversing the vast distances that currently limit human exploration of space. However, the existence of wormholes remains speculative. Although the general theory of relativity allows such structures to exist, they present several serious problems. First, for a wormhole to be passable, exotic matter, a material with negative energy density, would be required to keep the wormhole stable and open. The existence of exotic matter has not been confirmed, and creating or utilizing it, if possible, involves significant scientific and engineering challenges. Moreover, even if a stable wormhole could be created, the intense gravitational forces near the entrance could pose a serious danger to all potential travelers. Moreover, maintaining the stability of the wormhole from perturbations of particles and radiation passing through it is another major challenge. Calculations show that passable wormholes, if they exist, can be highly unstable and collapse rapidly in vivo. Practical considerations also include the energy requirements and technological advances needed to detect or create such cosmic phenomena, which are far beyond our current capabilities. Despite these difficulties, the study of wormholes continues to fascinate and stimulate research in theoretical physics. The concepts of quantum mechanics and the emerging field of quantum gravity may eventually provide new ideas or even technological avenues. Although wormholes currently belong to the realm of science fiction, they stimulate valuable discussions about the nature of space-time, the limits of human travel, and the fundamental laws governing our universe. Overall, while wormholes hold intriguing potential to revolutionize space travel, they remain a theoretical construct with numerous scientific and practical barriers that have yet to be overcome. Future discoveries in physics could either bring this concept closer to reality or open new ways to realize rapid space travel, continuing to fuel humanity's dreams of space exploration. Scientists study the curvature of space-time around massive objects using a combination of precise observations and sophisticated theoretical models based on the general theory of relativity. One basic method involves observing the effects of gravitational lensing. When light from a distant star or galaxy passes near a massive object, such as a black hole or a cluster of galaxies, the gravity of the massive object bends the path of the light. This curvature or lens can create multiple images of the same star, magnify a distant object, and even create arcs and rings of light. By analyzing these distortions, scientists can map the distribution and strength of the gravitational field, thereby drawing conclusions about the curvature of space-time in a particular region. Another method is to study the orbits of stars and planets around massive objects. For example, by tracking the orbits of stars near the supermassive black hole at the center of our galaxy, scientists can determine the mass of the black hole and the curvature of space-time around it. The most famous example is the orbit of the star S2 around the Milky Way's central black hole, the star Sagittarius A. The star's fast and curved trajectory indicates the presence of an intense gravitational field, which confirms the predictions of the general theory of relativity. More recently, the observation of a star's relativistic redshift as it approaches a black hole has provided more direct evidence of space-time curvature. Scientists also detect the curvature of space-time using gravitational waves, ripples created by massive accelerating objects such as merging black holes or neutron stars. Instruments such as LIGO and Virgo detect these waves, giving insight into the dynamics of the space around these cataclysmic objects. The resulting waveforms carry information about the mass and rotation of the bodies involved in the collision, as well as the nature of their collision, revealing the characteristics of space-time under extreme conditions. In addition, precise measurements of the orbits of satellites within our solar system by instruments such as Gravity Probe B have confirmed the presence of frame dragging and geodesic effects. Imperceptible shifts in the orientation of satellite gyroscopes caused by the mass and rotation of the Earth again confirm the predictions of the general theory of relativity. In all of these cases, the interplay between observational data and theoretical models allows scientists to deeply understand the curvature of space-time around massive objects. This not only confirms Einstein's theories, but also deepens our understanding of fundamental properties of the universe, from the behavior of black holes to the dynamics of galaxy clusters, and potential insights into new physics beyond our current models. Space-time singularities, mysterious points where gravitational forces become infinite and the known laws of physics cease to apply, are surrounded by deep mysteries that challenge our understanding of the universe. The best-known examples of singularities are found at the centers of black holes and at the very beginning of the universe, similar to the Big Bang. These regions are characterized by space-time densities and curvatures that are so extreme that standard notions of space and time are shattered. One of the most puzzling aspects of singularities is their very existence in solutions to the equations of Einstein's general theory of relativity. These equations predict that under certain conditions, such as the collapse of a massive star, the gravitational field can become so strong that space-time is curved infinitely. However, this prediction leads to the destruction of determinism, where the future and past states of physical processes can no longer be accurately predicted. The naked singularity and scenario contradicts the cosmic censorship hypothesis proposed by physicist Roger Penrose, according to which singularities must always be hidden in event horizons beyond which they cannot affect the observable universe. Another important mystery associated with singularities is the interaction between general relativity and quantum mechanics. General relativity theory successfully describes the macroscopic world of stars, galaxies, and the cosmos as a whole, while quantum mechanics does an excellent job of explaining microscopic phenomena such as particle interactions. However, these two pillars of modern physics are fundamentally incompatible in situations involving extreme gravitational fields and very small scales, such as singularities. A fully developed theory of quantum gravity that seamlessly integrates these two systems is necessary to resolve the paradoxes associated with singularities. Hypotheses such as string theory and loop quantum gravity have sought to address these questions, but a definitive solution remains elusive. These mysteries are exacerbated by an information paradox that is particularly significant for black hole singularities. According to the classical general theory of relativity, any information that enters a black hole is lost to the external universe and is only preserved in the singularity. However, quantum mechanics states that information cannot be annihilated. Reconciling these conflicting views challenges existing theories and leads to various speculative ideas, such as the holographic principle, which suggests that information in a volume of space can be thought of as encoded at the boundary of that space. Finally, the Big Bang singularity presents its own set of questions. As the universe approaches the initial singularity, it becomes incredibly hot and dense, and classical explanations collapse. What existed before the Big Bang and what caused it are deep mysteries that are currently beyond the control of observational science, and they are deeply intertwined with the search for a unified theory. Singularities are thus at the frontier of physics, representing both the limits of our current theories and the tantalizing promise of deeper understanding. These cosmic mysteries force us to push the boundaries of cognition, stimulating ongoing attempts to develop a more complete and unified description of the universe. Particle gas pedals are sophisticated tools that allow us to understand the fundamental nature of matter and space-time. By accelerating particles to nearly the speed of light and colliding them, these machines recreate conditions similar to those just after the Big Bang, allowing scientists to explore the fundamental forces in particles that make up the universe. One of the most famous examples is the Large Hadron Collider, LHC, operating at CERN, which accelerates protons and heavy ions to enormous energies and then collides them with each other. High-energy collisions produce many particles, some of which exist only fleetingly under ordinary conditions. By studying these particles and their interactions, scientists can test and refine the standard model of particle physics, the theory that describes the electromagnetic, weak and strong nuclear interactions. The discovery of the Higgs boson at the LHC in 2012 confirmed one of the most important aspects of this model, clarifying how particles acquire mass through the Higgs mechanism. This breakthrough has impacted our understanding of space-time by providing insight into the field that permeates the universe and influences the structure of the cosmos itself. In addition, particle gas pedal experiments investigate phenomena that may provide clues to the nature of space-time on extremely small scales. For example, studying proton-proton collisions at very high energies could potentially reveal deviations from the standard model, hinting at new physics such as supersymmetry or extra dimensions. Theories beyond the standard model, including string theory, suggest that space-time may have more than just the familiar 4 dimensions, 3 spatial and 1 temporal. High-energy collisions can produce particles or effects that indicate the existence of these extra dimensions, which has direct implications for our understanding of the underlying structure of the universe. Particle gas pedals also explore the properties of quark-gluon plasma, a state of matter thought to have existed microseconds after the Big Bang. Heavy ion collisions allow physicists to recreate and study this plasma, which provides valuable insights into the behavior of strong nuclear forces at extremely high temperatures and densities. Understanding these forces and states of matter helps piece together the early evolution of the universe, giving a clearer picture of how space-time and fundamental forces evolved. In addition, particle gas pedals make it possible to simulate the conditions under which the principles of quantum field theory and general relativity are tested. For example, predictions about how particles should behave in strong gravitational fields can be compared to observed behavior in high-energy collisions, offering an indirect test of the mutual consistency of these theories. This is fundamental to advancing toward a theory of quantum gravity, a goal that seeks to unify general relativity and quantum mechanics. Particle gas pedals serve as both microscopes and time machines, allowing us to explore the deepest layers of reality and the earliest moments of the universe. Through these experiments, scientists are not only confirming existing theories, but also discovering new phenomena, pushing the boundaries of our knowledge of space-time and the myriad forces that shape the cosmos. The theoretical implications of FTL travel are profound and far-reaching, touching the very foundations of physics and our understanding of the universe. According to Einstein's special theory of relativity, when an object approaches the speed of light, its mass effectively becomes infinite, and the energy required to accelerate it further grows without limit. It follows that FTL travel, at least as conventionally understood, is fundamentally impossible. However, speculative concepts explore the implications and theoretical underpinnings that could enable FTL travel. One of the most famous hypothetical designs is the concept of a warp drive, inspired by a 1994 proposal by Miguel Alcubierre. Alcubierre's model suggests that it is possible to compress space-time in front of a spacecraft and expand it behind, allowing the craft to traverse space-time waves, thus traveling faster than light relative to outer space, but not locally breaking the light speed barrier. At the same time, relativity is preserved because, The spacecraft itself is not traveling faster than light in its local space-time bubble. However, it requires exotic matter with negative energy density, the existence of which has not been proven, and its use is not possible. Another speculative avenue involves wormholes or Einstein-Rosen bridges. If these hypothetical structures could be stabilized, they could serve as shortcuts through space-time, potentially allowing instantaneous travel between distant points. However, the stability and creation of passable wormholes would require exotic conditions of matter and energy that are currently beyond our technological and theoretical capabilities. The theoretical implications of such FTL mechanisms, if they could exist, are astounding. FTL travel would defy cause and effect, the principle that what causes happens first. The theory of relativity suggests that FTL travel could lead to situations where effects can occur before causes, potentially leading to paradoxes such as traveling back in time. This raises difficult questions about the nature of time and reality itself, requiring new physics or revised interpretations of existing theories. Furthermore, the existence of travel at faster than the speed of light would revolutionize our understanding of distances and connections in space. Interstellar and even intergalactic travel could become conceivable, fundamentally altering our view of the size of the universe and our place in it. Such possibilities will have profound implications for the search for extraterrestrial life, the colonization of other planetary systems, and the ultimate future of humanity. Interestingly, some recent theoretical advances in quantum mechanics suggest phenomena that may mimic some features of superluminal communications, such as entanglement, where particles act in interconnection instantaneously over vast distances. However, these "spooky actions at a distance," as Einstein called them, do not actually transmit information faster than light, and thus do not violate relativity. In sum, while the concept of FTL travel remains in the realm of theoretical speculation and science fiction, its implications are deeply intertwined with the fundamentals of physics. Exploring these ideas, whether through warp drives, wormholes, or quantum phenomena, forces us to rethink the nature of space, time, and the universe itself. Such research is pushing the boundaries of current scientific knowledge, potentially leading to revolutionary breakthroughs or a profound new understanding of the cosmos. String theory, the main contender for a unified theory of quantum gravity, is an exciting reconfiguration of the traditional concept of space-time. At its core, string theory posits that the fundamental entities in the universe are not point particles, as traditionally believed in particle physics, but one-dimensional strings that can oscillate in different modes. The vibrations of these strings correspond to different particles, where each mode of vibration represents a different kind of particle. The move to one-dimensional strings has profound implications for our understanding of space-time. First, string theory requires additional dimensions beyond the usual 3 dimensions of space and 1 dimension of time. Although the exact number of dimensions can vary depending on the particular formulation of string theory, the most commonly studied versions assume 10 or even 11 dimensions. These extra dimensions cannot be observed directly because they are thought to be compressed or folded on such a small scale that they are effectively hidden from current experiments. The existence of extra dimensions offers potential solutions to a number of physical problems. For example, it provides a framework for unifying all fundamental forces, including gravity, in a single theoretical architecture. The traditional general theory of relativity does not treat gravity as a curvature of 4-dimensional space-time caused by mass and energy. In string theory, gravity is still a manifestation of space-time geometry, but now in the context of a higher dimension. This higher dimensional space-time can manifest itself in many different forms, leading to different physical laws in contexts of different dimensions. In addition, the higher dimensionality of string theory allows us to resolve conflicts between general relativity and quantum mechanics. In the classical four-dimensional framework, singularities, such as in black holes or the Big Bang, can lead to infinity, which violates physical laws. The extended structure of string theory, through mechanisms such as string interactions and the inclusion of extra dimensions, can smooth out these singularities, potentially avoiding meaningless infinities and providing a more consistent quantum theory of gravity. One of the most intriguing aspects of the space-time implications of string theory has to do with D-branes, the multidimensional objects of the theory to which strings can attach their endpoints. These branes introduce new dynamics and lead to scenarios in which our universe may be a four-dimensional slice within a higher dimensional space. This scenario, often referred to as the brane world hypothesis, opens the door for phenomena such as gravity leaking into extra dimensions, offering a potential explanation for the relative weakness of gravity compared to other fundamental forces. In addition, string theory revives the idea of dualities, connections that indicate that seemingly different physical scenarios are actually equivalent when properly considered. These dualities could link different types of string theories or even connect higher and lower dimensional theories, suggesting that space and time may be emergent properties rather than fundamental constructs. This concept further changes our understanding of the very fabric of reality. String theory revolutionizes the concept of space-time by introducing additional dimensions, proposing new fundamental entities, and offering a unified structure that reconciles gravity with quantum mechanics. These innovations not only challenge traditional notions, but also provide fertile ground for solving some of physics' deepest mysteries, potentially leading to a deeper and more comprehensive understanding of the universe. In the field of relativity theory, one of the deepest and most perplexing questions still unanswered is the harmonization of general relativity theory with quantum mechanics. The general theory of relativity, formulated by Albert Einstein, perfectly describes gravity as a curvature of space-time itself, affecting large and small masses. On the other hand, quantum mechanics governs the microscopic world with remarkable precision, explaining the behavior of particles at the smallest scales. However, these two systems operate on fundamentally different principles that are not easily synthesized. The task of unifying these two giants into a coherent theory of quantum gravity is an enigma that has puzzled physicists for decades. This quest is opening up deeper layers of reality, perhaps revealing the nature of black holes, the origin of the universe, and the structure of space-time at the Planck scale, a mind-bogglingly tiny scale where classical and quantum effects are thought to merge. Another tantalizing mystery in the study of relativity is the true nature of dark energy and dark matter. Observations have shown that ordinary matter, of which stars, planets, and all visible structures are composed, accounts for only about 5% of the total energy content of the universe. A staggering 70% is attributed to dark energy, the unknown force causing the accelerated expansion of the universe, while dark matter accounts for about 25%, influencing the formation and clustering of galaxies through its gravitational influence. Despite knowing their significant role, scientists are still in the dark, literally, about the composition and mechanisms of these invisible entities. Understanding dark energy and dark matter could fundamentally change our understanding of not only the theory of relativity, but also the fundamental structure of the universe, painting a more complete picture of the past, present, and future of the universe. Dark matter is an elusive and mysterious substance that does not emit, reflect, or absorb light, making it invisible to modern telescopes. Although it is invisible, it exerts a gravitational pull that affects the motion of galaxies and galaxy clusters. It is estimated that about 85% of the total mass of the universe is dark matter, suggesting that the ordinary matter we observe, from stars to planets, makes up only a tiny fraction of the pillar of the universe. The discovery of dark matter dates back to the early 20th century. In the 1930s, Swiss astronomer Fritz Zwicky observed a cluster of galaxies in the form of a coma and discovered that the galaxies were moving too fast to be held together by visible matter alone. He coined the term Dunkelmarie to describe this invisible mass, which means dark matter and dark matter. Vera Rubin obtained even more convincing evidence in the 1970s when she studied the rotation curves of spiral galaxies. Rubin found that stars on the outer edges of galaxies rotate as fast as stars in the center, a phenomenon that cannot be explained by the presence of visible matter alone. It suggests that there is a significant amount of invisible mass exerting a gravitational influence. Modern technological advances continue to shed light on dark matter, albeit indirectly. Observatories such as the Hubble NDAMP. Space Telescope have provided insight into it through gravitational lensing, where light from distant galaxies is deflected by the massive invisible objects between them and us. Although scientists have not yet been able to directly detect dark matter particles, numerous experiments are currently underway to determine what dark matter is actually made of, with hypotheses ranging from WIMPs, weakly interacting massive particles, to axions. Understanding dark matter remains one of the most pressing and tantalizing challenges in cosmology today, which promises to redefine our understanding of the structure and evolution of the universe. Dark matter plays a key role in shaping the structure of the universe on both large and local scales. The influence of dark matter is ubiquitous and shapes the cosmos, from the formation of galaxies to the behavior of entire galaxy clusters. Because of its invisible nature, the presence of dark matter is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. In the early universe, shortly after the Big Bang, dark matter acted as a cosmic framework around which ordinary matter could gather. This matter contributed to the formation of the first galaxies and galaxy clusters. Without the gravitational pull of dark matter, the gas needed to form stars, and galaxies would not be compressed as efficiently. The so-called cosmic web, a vast network of filaments composed mostly of dark matter that connects galaxies and clusters, demonstrates how dark matter organizes matter on the largest scales. These strands of dark matter attracted ordinary matter, guiding the formation and distribution of galaxies and intergalactic gas along their length. On smaller scales, dark matter also influences the internal dynamics of galaxies. Observations of the rotation curves of spiral galaxies, where stars at the outer edges rotate faster than the apparent mass alone predicts, indicate the presence of a vast amount of invisible mass, dark matter, extending far beyond the visible edges of these galaxies. This invisible halo of dark matter stabilizes galaxies, preventing them from being torn apart by their rapid rotation. Consequently, dark matter is fundamental to the formation, structure, and ultimate fate of the universe. Understanding its properties and interactions remains one of the most exciting challenges of cosmology. As we learn more about dark matter, we will inevitably gain a deeper understanding of the evolution of cosmic structures and the very structure of the universe, as well as open up new areas of physics beyond our current knowledge. The detection of dark matter, given its elusive nature, is one of the most intriguing challenges in modern science. Because dark matter does not emit, absorb, or reflect light, scientists rely on indirect methods to determine its presence and properties. One of the main ways to detect it is to observe its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Gravitational lensing is a powerful tool for detecting dark matter. When light from distant galaxies passes through a cluster of galaxies, The cluster's enormous gravitational field, which includes a significant dark matter component, bends the light, distorting and magnifying the image of background galaxies. By mapping these distortions, astronomers can draw conclusions about the distribution and amount of dark matter in a cluster. Lensing often reveals more mass than can be seen, suggesting the presence of dark matter. Another method involves the rotation curves of galaxies. When astronomers like Vera Rubin studied the rotation rate of stars in spiral galaxies, they found that stars on the outer edges of these galaxies rotate as fast as they do near the center, contradicting expectations based solely on observed matter. This uniform rotation rate suggests the existence of a halo of dark matter enveloping the galaxies and providing the extra gravitational pull needed to keep the stars moving so quickly. On a more experimental front, scientists are using underground detectors to capture potential dark matter particles. Direct detection experiments, such as those using cryogenic detectors or liquid xenon targets in facilities such as the Large Underground Xenon Experiment, LOX, aim to observe rare interactions between dark matter particles and ordinary matter. When a dark matter particle collides with a nucleus in a detector, it can release a minuscule amount of energy in the form of light or heat that sophisticated instruments can detect. Finally, particle gas pedals such as CERN's Large Hadron Collider, LHC, investigate the existence of dark matter by colliding protons at high energies. Collisions can create dark matter particles. Whether or not they can be detected can be judged by the lack of energy and momentum in the particle tracks obtained. Although dark matter has not been directly observed, these techniques provide strong evidence for its existence and continue to elucidate its possible properties. The quest to directly detect dark matter remains an exciting area of the ever-evolving field of cosmology that promises to reveal new aspects of our understanding of the universe. The composition of dark matter remains one of cosmology's most tantalizing mysteries, and several leading theories have emerged to explain its elusive nature. According to one of the most common theories, dark matter consists of weak or weakly interacting massive particles. It is believed that these hypothetical particles were produced in large quantities in the early universe and could explain the vast amount of invisible mass based on their weak interactions with ordinary matter and electromagnetic radiation. WIMPs are attractive because they fit well within the standard model of particle physics and its extensions, such as supersymmetry, which predicts the existence of such particles. Another compelling candidate is the axion, a particle first proposed in the late 1970s as a solution to the strong CP problem in quantum chromodynamics. Axions, if they existed, would be very light and would have very little interaction with ordinary matter, making them difficult to detect. These may have appeared in the early universe in sufficient quantities to explain dark matter, and they are being actively searched for in experiments such as the Axion Dark Matter Experiment, ADMX, and other initiatives. Sterile neutrinos are another interesting possibility. Unlike known active neutrinos, which interact via the weak nuclear interaction, sterile neutrinos interact only via gravity. Their mass could help explain the observed properties of dark matter and play a role in the formation of large-scale structures in the universe. The discovery of sterile neutrinos would have profound implications for our understanding of dark matter and elementary particle physics. There are also more exotic theories, such as the idea that dark matter is made up of primordial black holes. These black holes may have formed in the early stages of the universe due to strong density fluctuations. Although they are difficult to detect, they may contribute to gravitational effects caused by dark matter. In addition, some theories suggest that dark matter may not be composed of particles, but rather a variation of the known laws of gravity. One such theory is modified Newtonian dynamics, MOND, which proposes to modify Newton's laws on cosmic scales to account for the missing mass in the universe. However, This idea is less popular because it cannot explain observations on different scales as fully as particle-based theories of dark matter. Each of these theories has been the subject of rigorous experimental and observational study. Progress in this field not only promises to solve the mystery of dark matter, but may also reveal new physics that could overturn our view of the universe. Dark energy and dark matter are two of the most enigmatic components of our universe, each playing a separate and key role in its evolution, yet radically different in their nature and effects. Together, they make up about 95% of the universe, with dark energy making up about 70% and dark matter about 25%. Dark matter is a form of invisible mass that exerts a gravitational influence, contributing to the formation and clustering of galaxies and galaxy clusters. The gravitational influence of galaxies helps them maintain their integrity, providing the extra mass needed to explain the observed rotational velocities of stars on the outskirts of these galaxies. Although dark matter does not interact with electromagnetic forces, making it invisible to light, it is still compressed by gravity, guiding the formation of large-scale cosmic structures in the universe. Dark energy, on the other hand, is a mysterious force that appears to drive the accelerated expansion of the universe. Dark energy, first discovered in the late 1990s through observations of distant type Ia supernovae, acts as a kind of anti-gravity, counteracting the attractive force of gravity on cosmic scales. Unlike dark matter that clusters together, dark energy is thought to be uniformly distributed in space, affecting the geometry of the universe and its rate of expansion. The nature of dark energy remains one of the central mysteries of modern cosmology, and it is often modeled through the cosmological constant, a term introduced by Einstein, or through more dynamical fields such as quintessence. The influence of dark energy is most obvious when considering the large-scale structure of the universe and the rate of its accelerated expansion. It stretches space itself, affecting the rate at which galaxies move away from each other. This accelerating expansion has profound implications for the future of the universe, suggesting that it could continue to expand forever, leading to a cold, dark, and increasingly diffuse cosmos. While dark matter binds galaxies and clusters together through its gravitational attraction, dark energy pushes them apart, dominating the dynamic evolution of the universe on the largest scales. Understanding both phenomena is crucial to gaining a complete understanding of the origin, structure, and ultimate fate of the universe. Researchers continue to use a range of observational strategies, including measurements of the cosmic microwave background, large-scale galaxy surveys, and gravitational lensing studies to explore these dark components and unravel their mysteries. Dark energy has a profound effect on the expansion of the universe, acting as a mysterious force that accelerates that expansion. This discovery, which refutes previous ideas about slowing cosmic expansion, came from observations of far-infrared supernovae in the late 1990s. These supernovae, considered standard candles because of their constant intrinsic brightness, have allowed astronomers to measure distances to distant galaxies. They found that galaxies are not just moving away from us, but are accelerating in their distance, meaning that some unknown force is pushing them apart at an increasing rate. The role of dark energy in the accelerated expansion of the universe can be understood through its effect on space-time itself. Unlike ordinary and dark matter, which bind together and exert a gravitational attraction, dark energy is thought to have a repulsive effect. It is uniformly distributed throughout the universe, resulting in a constant energy density even as space expands. This characteristic can be modeled as the cosmological constant, denoted by the Greek letter L Lyru, in the field equations of Einstein's general theory of relativity, denoting the form of vacuum energy that permeates all of space. Since dark energy dominates the energy composition of the universe, its repulsive force dominates the gravitational pull of matter. As a result, the fabric of space-time is stretched, accelerating the rate of expansion of the universe. Modern measurements show that dark energy makes up about 70% of the total energy content of the universe, resulting in an accelerated expansion that at first seemed counterintuitive to many cosmologists. The consequences of this accelerated expansion are profound. As time goes on, galaxies will move farther apart, and the observable universe will become more and more isolated. This phenomenon could lead to a big freeze scenario where galaxies go over the horizon and become unobservable. Stars burn up, and the universe cools to the point where thermodynamic activity ceases. Another intriguing possibility is the Big Rip, an event in the distant future in which the influence of dark energy becomes so strong that it eventually tears galaxies, stars, and even atomic structures apart. Research is now underway to better understand dark energy, using techniques such as studying the cosmic microwave background radiation, analyzing large-scale surveys of galaxies, and observing gravitational lensing effects. By understanding the nature of dark energy, scientists hope to uncover deeper truths about the fundamental forces shaping our cosmos, and perhaps open up new areas of physics that lie beyond our current understanding. The strongest evidence for the existence of dark energy comes from a variety of astronomical observations and measurements that consistently point to an accelerated expansion of the universe. Taken together, all this evidence creates a coherent picture of dark energy as the dominant force in the cosmos. Some of the first and most compelling evidence came from the study of distant IA supernovae. In the late 1990s, two independent research groups, the Supernova Cosmology Project and the High Z Supernova Search Team, observed these supernovae as standard candles due to their uniform intrinsic brightness. By measuring apparent brightness and redshift, scientists have found that distant supernovae are systematically darker than expected. This decline suggests that the rate of expansion of the universe has accelerated over the past billions of years, implying the existence of a repulsive force called dark energy that opposes gravity. Another important piece of evidence concerns the cosmic microwave background, relic radiation, and Big Bang remnants. The Wilkinson Microwave Anisotropy Probe, WMEP, and the Planck satellite have measured the relic emission with unprecedented precision. The results show small fluctuations in temperature that provide a better understanding of the early universe. By analyzing these fluctuations, scientists can determine the shape of the universe and its overall energy content. Measurements of relic radiation show that the universe is flat, implying a certain overall energy density. However, visible matter, dark matter, and radiation together account for only about 30% of this density, suggesting that the remaining 70% must come from dark energy. Large-scale studies of galaxy structure provide additional support. Projects such as the Sloan Digital Sky Survey, SDSS, map the distribution of galaxies in the universe. These studies help trace the large-scale structure of the universe and the patterns of galaxy clusters. Observations show that galaxies are not only moving away from each other, but also accelerating. This acceleration is consistent with the presence of dark energy. Additional confirmation is provided by the phenomenon of baryonic acoustic oscillations, BAO. In the early universe, pressure waves propagated through hot plasma, leaving marks on the distribution of galaxies. These marks, or sonic peaks, serve as cosmic benchmarks. By measuring the distance between these peaks in the distribution of galaxies, astronomers can trace the expansion history of the universe. BAO measurements are consistent with an accelerating universe driven by dark energy. Finally, gravitational lensing, in which light from distant objects is deflected by large structures in the foreground, also provides evidence. By studying how galaxies and galaxy clusters refract light from background sources, scientists can infer the distribution of dark matter and dark energy. The results support a model of the universe dominated by dark energy, which affects the overall mass-energy balance and expansion rate. Together, these diverse and converging lines of evidence provide compelling evidence for the existence of dark energy, profoundly changing our understanding of cosmology and the evolution of the universe. The potential interaction between dark matter and dark energy is a topic that raises some of the deepest questions about the composition and evolution of the universe. Although both of these phenomena are of great importance to our understanding of cosmology, they have fundamentally different properties and roles. Dark matter, with its gravitational coupling, serves as the basis of cosmic structures, while dark energy drives the accelerated expansion of the universe. In the current cosmological model, the standard cold dark matter lambda model, LCDM, dark matter and dark energy, are generally considered as separate and non-interacting components. Dark matter contributes to the formation and stability of galaxies and clusters through its gravitational attraction, while dark energy, often modeled as the cosmological constant lambda, exerts a uniform repulsive effect on all of space, causing cosmic acceleration. However, some theoretical models suggest potential interactions between dark matter and dark energy. These interactions can alter the behavior of both components over cosmic time. One such model includes the notion of bound dark energy, where the density of dark energy changes with time, potentially interacting with dark matter in ways that alter its properties or distribution. For example, dark energy can decay into dark matter particles or vice versa, which affects the relative amount and distribution of these substances in the universe. Another interesting model is scalar field dark energy, in which dark energy is described by a dynamical scalar field rather than a constant quantity. In these models, the scalar field can interact with dark matter, affecting its clustering behavior and the overall dynamics of cosmic structures. This interaction can lead to observable features in the large-scale structure of the universe, such as changes in galaxy clustering or variations in the cosmic microwave background radiation. Experimental and observational work has not yet provided definitive evidence of such interactions. However, precise measurements of the cosmic microwave background, galaxy clustering, baryonic acoustic oscillations, and the distribution of large-scale structures continue to break new ground. For example, deviations from expected behavior in these observations may hint at interactions between dark matter and dark energy. Another area of research is high-energy particle physics experiments, which may reveal new particles or forces that could mediate the interaction between dark matter and dark energy. Experiments at facilities such as the Large Hadron Collider, LHC, and various dark matter detection experiments can provide indirect evidence of such interactions by revealing anomalies that cannot be explained by the existing model. Although the standard cosmological model currently treats dark matter and dark energy as independent, conceptual models and current research are exploring the possibility of their interaction. The discovery of any such interactions will greatly expand our understanding of these enigmatic components and could lead to revolutionary changes in our understanding of the fundamental forces of the universe and the underlying physics. Understanding the true nature of dark energy presents many challenges, both observational and theoretical, that scientists are striving to overcome. These challenges stem from the elusive properties of dark energy and the limitations of our current models and technologies. One of the main challenges is its detection and direct measurement. Unlike dark matter, which has a gravitational effect observed through its influence on galaxies and cosmic structures, the influence of dark energy is more subtle, manifested primarily in the accelerated expansion of the universe. This acceleration can be inferred from indirect observations such as redshifts of distant type Ia supernovae and patterns in the cosmic microwave background radiation. These methods, while reliable, do not directly measure dark energy, leaving its nature somewhat ambiguous. Adding to the difficulty is the fact that dark energy makes up about 70% of the energy density of the universe. Yet it remains uniformly distributed and does not stick together like ordinary or dark matter. This large-scale homogeneity makes it difficult to isolate distinct regions of space where the influence of dark energy can be individually studied, which complicates the design of experiments capable of investigating its properties. From a theoretical perspective, integrating dark energy into the existing framework of physics presents significant challenges. The most commonly used model, the cosmological constant lambda, represents dark energy as a constant energy density in a vacuum. This model, while consistent with current observations, suffers from the cosmological constant problem. This problem arises because the value of vacuum energy predicted by quantum mechanics is much higher than the observed value. Bridging this huge gap remains one of the deepest unsolved problems in theoretical physics. Other theories suggest that dark energy may be an entity-like dynamic field. This field varies in time and space, potentially interacting with other cosmic components, such as dark matter. However, these models introduce additional parameters and complexities, making them more difficult to test and validate against observations. Moreover, the theoretical tools needed to fully describe these dynamical fields often require extensions of the standard model of particle physics or modifications of the general theory of relativity, which creates a contradiction with established physical laws. The accuracy of cosmological measurements is also a challenge. Observing the universe with the precision needed to determine the properties of dark energy requires next-generation telescopes and instruments. Projects such as the Dark Energy Survey, DES, and the Euclid mission are designed to map large areas of the sky with high precision. But interpreting data from these large-scale surveys requires sophisticated statistical tools and deep theoretical understanding. Finally, reconciling dark energy with other fundamental forces and particles may require new physics that goes beyond existing paradigms. This may involve additional dimensions, modifications to Einstein's theory of gravity, such as FR gravity or scalar tensor theories, or entirely new kinds of particles and interactions. Developing and testing these ideas remains a challenge, requiring advances in both experimental techniques and theoretical foundations. The quest to understand dark energy is hampered by its indirect detection, the theoretical problems associated with its incorporation into established physics, the need for accurate cosmological measurements, and the potential need for new physics. Despite these obstacles, ongoing research promises to unravel this profound mystery, and each new observation and experiment brings us one step closer to understanding the true nature of dark energy. The impact of dark matter and dark energy goes far beyond their role in shaping the large-scale structures of the cosmos. These enigmatic components also significantly affect the ultimate fate of the universe. Understanding their interrelationships is essential for predicting how the universe will evolve and what it may eventually become. Dark matter, which makes up about 25% of the energy density of the universe, acts as the basic gravitational framework around which galaxies and galaxy clusters form. Its gravitational pull helps bind these cosmic structures together, counteracting the dispersive effect of the expansion of the universe. The presence of dark matter has allowed galaxies to cluster and persist for billions of years, forming the rich and diverse cosmic landscape we see today. In contrast, dark energy, which makes up about 70% of the energy density of the universe, acts as a repulsive force that contributes to the accelerated expansion of the universe. Its influence was made clear by observations of distant Type Ia supernovae in the late 1990s, which showed that the rate of expansion of the universe is not slowing down, but rather accelerating. This acceleration suggests that dark energy works against gravity, causing space itself to stretch at an ever-increasing rate. The balance between dark matter and dark energy will ultimately determine the fate of the universe. If dark energy continues to dominate, expansion will accelerate indefinitely, leading to what is often referred to as the Big Freeze or heat death. In such a scenario, galaxies would become increasingly distant from each other, stars would burn out, and the universe would become increasingly colder and darker as it expands. Over trillions of years, the remaining cosmic structures would become isolated and the residual heat would dissipate, leading to a state of thermodynamic equilibrium in which no meaningful physical processes would occur. An even more extreme option is the Big Bang scenario. If the repulsive force of dark energy becomes stronger over time, which contradicts the current cosmological constant model, the acceleration could increase to the point where it would tear galaxies, stars, planets, and eventually even atomic structures apart, splitting all matter in the universe. This would lead to a cataclysmic event that would result in space-time itself being torn apart. Conversely, if dark matter or a future understanding of dark energy reveals new physics that balances this acceleration, the universe could reach a steady state or even undergo a major crisis. In this scenario, expansion would eventually stop and reverse, leading to contraction, culminating in a singularity, possibly followed by a new Big Bang, according to some speculative models. In addition, theoretical models that study dynamic forms of dark energy, such as quintessence, offer more subtle possibilities. Such options include oscillating universes, in which periods of expansion and contraction follow each other cyclically, or scenarios in which dark energy diminishes over time, allowing gravitational forces to regain dominance. Current observations and cosmological data, such as cosmic microwave background radiation, large-scale structural studies, and supernovae measurements, strongly support a future dominated by dark energy and accelerating expansion. However, as research continues, our understanding of these dark components may change, which could lead to new discoveries and changes in our long-term predictions of the evolution of the universe. Although dark matter binds the universe together with its gravity, dark energy accelerates its expansion. The balance between these forces not only shapes the current structure of the universe, but also determines its future trajectory, offering diverse and profound possibilities from an ever-expanding universe to a cold and dark fate to more dramatic and speculative outcomes. In the first fraction of a second after the Big Bang, the universe was too hot and dense for any particles or atoms to exist. It was filled with quark-gluon plasma, a state of matter in which quarks, the fundamental particles that later formed protons and neutrons, were not encased in atomic nuclei, but were in a free state in a soup of gluons, particles mediating the strong force holding quarks together. As the universe expanded and cooled, it reached a temperature at which quarks could combine to form protons and neutrons, the building blocks of atomic nuclei. This epoch, known as the hadronic epoch, occurred within the first microsecond to 1 second after the Big Bang. The formation of protons and neutrons was a turning point in the early universe, laying the groundwork for the creation of more complex forms of matter. After the hadronic age, the universe continued to cool, leading to the lepton age, which lasted from 1 second to a few minutes after the Big Bang. At the time, leptons, like electrons, were the dominant form of matter. The universe was still too hot for protons and neutrons to combine with electrons to form a nucleus. The most important particle formation event took place: nucleosynthesis, a process that occurred in the first few minutes after the Big Bang. During this time, the universe cooled so much that protons and neutrons began to combine to form the nuclei of the simplest elements: hydrogen, helium, and small amounts of lithium and beryllium. Primordial nucleosynthesis produced most of the helium in the universe, along with hydrogen that had not bound into helium nuclei. It is important to note that these were not yet full atoms as we imagine them today. Electrons orbit around a nucleus. The universe was still too hot for electrons to be captured into orbits around nuclei to form neutral atoms. The formation of neutral atoms, a process known as recombination, would not occur until 380,000 years after the Big Bang, leading to the separation of matter and radiation and the emission of the cosmic microwave background radiation. The afterglow of the Big Bang gives us a glimpse of what the universe was like at that time. Now, let's delve into that exciting era, when the fundamental forces of nature began to delineate and define the evolving cosmos. This history of separation is a cornerstone in understanding the complex tapestry of the universe, from its most nascent moments to the richly structured space we observe today. Initially, in the first moments of the universe's existence, all the forces were combined into a single force, indicating the extreme conditions of temperature and density that the cosmos was under. As the universe expanded and cooled, this primordial unity split in a series of symmetry-breaking events, giving rise to the various forces we know today. Gravity, electromagnetism, strong nuclear forces, and weak nuclear forces. The first to separate was gravity, which emerged as a separate force when the universe cooled from its incomprehensibly hot and dense state. This separation is hypothesized to have occurred just a fraction of a second after the Big Bang, marking the universe's first step toward the complex force interactions that govern it now. The separation of gravity laid the foundation for the large-scale structure of the cosmos, directing the formation of galaxies, stars, and planets, forming the very fabric of the universe. After gravity split, the great unified force, which included the electromagnetic strong and weak nuclear forces, remained in its unified state until the universe cooled further. When the temperature dropped to a critical point, the strong nuclear force, which is responsible for binding quarks within protons and neutrons and maintaining the integrity of atomic nuclei, separated from the electroweak force, which is a combined form of the electromagnetic and weak nuclear forces. This separation, which occurred about 10 circles 36 to 10 circles 32 seconds after the Big Bang during the epoch of cosmic inflation, laid the groundwork for the formation of the first particles of the universe. Electroweak forces continued to govern the energy landscape of the universe until they, too, underwent symmetry breaking. As a result of this event, which occurred about 10 near-flexible 12 seconds after the Big Bang, the electroweak forces separated into the electromagnetic forces mediated by photons and the weak nuclear forces responsible for radioactive decay and nuclear fusion processes in stars. This separation finalized the composition of the fundamental forces, creating the conditions for further cooling of the universe, which allowed the formation of more complex particles and eventually atoms. The separation of the fundamental forces during the formation of the universe was a pivotal event that created the diversity of matter and structures observed in the cosmos today. Moving from the pivotal moments when the fundamental forces of nature began their gradual separation, we delve into the significance of the electroweak epoch, a defining period in the evolution of the universe. This epoch represents a critical phase shortly after the Big Bang, during which the electromagnetic and weak nuclear forces, two of the four fundamental forces, were combined into a single force known as the electroweak force. The electroweak epoch occurred roughly between 10 circles 12 seconds and 10 circles 6 seconds after the Big Bang, when the universe was cooling down from its originally hot and dense state, but was still incredibly energetic and dynamic. The significance of the electroweak epoch lies in its role in shaping the early universe and laying the groundwork for the formation of matter as we know it. In that epoch, The universe was filled with a hot, dense plasma of quarks, leptons, and their antiparticles, and electroweak bosons mediating a single force. As the universe expanded and cooled, it reached a critical temperature that allowed the electroweak forces to undergo a symmetry-breaking event. This event led to the separation of the electromagnetic force, mediated by photons, from the weak nuclear force, mediated by the WB and Z bosons. This separation was a fundamental step in the maturation of the universe, providing a diversity of interactions that eventually led to the formation of atoms and, by extension, the structure of the cosmos. The electroweak epoch has profound implications for our understanding of particle physics and the Standard Model. The Higgs mechanism, predicted by the presence of the Higgs field, played a crucial role in this epoch. The interaction of particles with the Higgs field endowed them with mass, a process that became central to the symmetry-breaking event that separated the electromagnetic and weak nuclear forces. The 2012 discovery of the Higgs boson, a particle associated with the Higgs field, was key evidence supporting the theoretical framework describing the electroweak force and its significance. Quarks, the fundamental constituents of matter, are subject to the strong nuclear force, one of the four fundamental forces that became distinctly apparent early in the evolution of the universe. This force, also known as the strong interaction, is surprisingly powerful, but its influence only extends over a very short distance. At the moments of the universe's birth, it acted as the glue that bound quarks together in groups of three, forming baryons that included protons and neutrons, the building blocks of atomic nuclei. This process began when the universe cooled enough for the strong force to overcome the kinetic energy that had previously kept the quarks apart. In this cooler but still incredibly hot environment, quarks began to interact more closely, forming pairs known as quark-antiquark pairs and triplets, which later evolved into protons and neutrons. The proton is composed of two top quarks and one bottom quark, and the neutron is composed of two bottom quarks and one top quark. The particular combination of quarks determines the properties of a particle, including its charge. Protons carry a positive charge due to their quark composition, while neutrons are neutral. This stage in the evolution of the universe involved not only the birth of these particles, but also with the transition from a state where quarks could move freely, the quark-gluon plasma, to one where they were locked into themselves, protons and neutrons. This locking mechanism is crucial to the stability of matter as we know it. Without it, the complex structures that make up the universe, from atoms to galaxies, could not exist. The hadronization of quarks into protons and neutrons laid the foundation for the next stage of cosmic evolution, the era of nucleosynthesis, when the first atomic nuclei were formed. These early stages in the formation of matter, from the fundamental forces and particles shaped by the conditions of the early universe, are central to our understanding of cosmic history and the very matter that makes up the world around us. As the universe continued to expand and cool after the formation of protons and neutrons, it reached a temperature favorable to the fusion of these particles. During this epoch, which occurred about 3 minutes after the Big Bang, nuclear forces overcame the repulsive electromagnetic forces between positively charged protons, allowing them to combine with neutrons to form the nuclei of the simplest elements. The first hydrogen nuclei, protons, fused to form helium, as well as trace amounts of deuterium, heavy hydrogen, tritium, a radioactive form of hydrogen, and very small amounts of lithium and beryllium. The process of nucleosynthesis is very important for several reasons. First, it determined the initial content of the light elements in the universe. The proportions of hydrogen and helium formed during this time were measured in the modern universe and were remarkably consistent with the predictions of the Big Bang theory. one of the most important proofs of the theory itself. Second, these initial nucleosynthesis events set the stage for star formation. Stars that have completed the nuclear fusion cycle then form the heavier elements necessary for life and the complex structures of the universe. The importance of nucleosynthesis goes beyond the simple creation of atomic nuclei. It marked the transition of the universe from a state of simple particles and forces to a complex tapestry of matter. It was during this period that the universe took its first steps toward chemical diversity, beginning the long cosmic evolution that would eventually lead to the formation of planets, life, and the vast array of celestial phenomena that filled the cosmos. In our search for answers, we come to the next pivotal chapter in the early history of the universe, the formation of the first atoms. This epochal event, which occurred about 380,000 years after the Big Bang, marked the cooling of the universe to the point where electrons could bond with nuclei to form neutral atoms, a period known as recombination. The backdrop for this monumental shift was an expanding and cooling universe, emerging from its original state of extreme heat and density, which set the stage for the birth of atomic matter as we know it. As the universe cooled, protons and neutrons formed from quarks began to interact in nuclear fusion, creating the first simple nuclei in the nucleosynthesis stage. The nuclei of hydrogen, consisting of a single proton, and helium formed first, along with deuterium, heavy hydrogen, and lithium in minor amounts. These light elements formed the initial chemical abundance of the universe, establishing a primordial stage rich in hydrogen and helium, the simplest and most abundant elements in the cosmos. However, the universe remained too hot for electrons to remain bound to nuclei. They existed in a state of plasma of free electrons, scattering photons and making the universe opaque. As the universe continued to expand and cool, it eventually reached a temperature at which the energy of photons was no longer sufficient to ionize hydrogen. At this point, electrons began to combine with the hydrogen and helium nuclei to form the first stable atoms. This recombination process dramatically reduced photon scattering, allowing the universe to become transparent for the first time. The photons released at this point form the cosmic microwave background radiation, the relic radiation, which gives a snapshot of the universe at the moment of recombination. The formation of the first atoms was a turning point in the cosmic narrative, paving the way for the universe to transition from a hot, dense state to a cooler, structured state capable of supporting complex structures such as stars and galaxies. This marked the end of the dark ages of the universe, the time before the first stars appeared, and initiated the gravitational collapse of matter into the first stars and galaxies. These stars would later enrich the cosmos with heavier elements through stellar nucleosynthesis, seeding the universe with the ingredients needed for planets and life. Nucleosynthesis, the process that formed the natural abundance of chemical elements in stars, played a crucial role in creating the diversity of elements we see in the universe today. After the first atoms were formed, the universe consisted mainly of hydrogen and helium, the simplest and most common elements. However, the complex and diverse world around us, from the air we breathe to the materials that make up the Earth, and even the components of our own bodies, requires a much broader set of elements. Nucleosynthesis enabled the processes necessary to form these elements, acting like a cosmic furnace that transformed the pure simplicity of the early universe into a rich tapestry of chemical diversity. The process of nucleosynthesis took place in several stages and environments, beginning with the Big Bang itself. The nucleosynthesis of the Big Bang at the dawn of the universe produced the lightest elements, including hydrogen, helium, and small amounts of lithium and beryllium. However, This process failed to produce the heavier elements necessary for life and the structure of the cosmos. The next stage of nucleosynthesis occurred within stars. Stars are universal element factories, transforming light elements into heavier elements by nuclear fusion in their nuclei. During the life of a star, hydrogen nuclei burn to form helium, a process called hydrogen burning. As stars age and their cores heat up, helium turns to carbon, and in more massive stars this process continues, producing elements up to iron in successive stages of nuclear combustion, such as carbon burning, neon burning, oxygen burning, and silicon burning. However, a different set of processes is required to create elements heavier than iron, as these elements cannot be formed by synthesis in stellar cores under normal circumstances because of their energy requirements. Instead, processes such as the R process, the capture of fast neutrons, and the S process, the capture of slow neutrons, come into play, mainly during supernova explosions and in the outer envelopes of stars with an asymptotic giant branch, AGB. Supernova, the cataclysmic explosions that mark the death of massive stars, create the necessary conditions for the R process, in which a dense stream of neutrons is absorbed by atomic nuclei, resulting in the formation of many of the heavier elements of the periodic table. The S process occurs in the calmer environment of AGB stars, where neutrons are captured more slowly, allowing elements such as barium and lead to be created. The various elements formed by nucleosynthesis are eventually carried throughout the galaxy by stellar winds and supernova explosions, saturating interstellar clouds with the materials needed for the next generation of stars, planets, and ultimately life. This cycle of birth, nucleosynthesis, and death of stars, followed by the formation of new stellar systems, has enriched the universe with complex chemistry over billions of years. U-particle gas pedals are sophisticated machines that accelerate charged particles, such as protons or electrons, to high speeds and smash them together or against targets, creating conditions that mimic those just after the Big Bang. These revolutionary tools allow scientists to explore the fundamental properties of matter and the forces that govern the interactions between particles. By accelerating particles to nearly the speed of light and then colliding them, particle gas pedals allow researchers to split atomic components into their constituent parts, discovering particles and phenomena not normally observed. The operation of a particle gas pedal is to use electric fields to accelerate particles and magnetic fields to guide and focus them along a given trajectory, which may be circular, as in synchrotrons and storage rings, or linear, as in linear gas pedals, LINEX. Many new particles are produced when these high-energy particles collide, allowing scientists to study the rules of particle physics in an environment with extreme energy densities similar to those that existed just after the Big Bang. There are several types of particle gas pedals, each serving a different purpose in the field of research and beyond. For example, the Large Hadron Collider, LHC, at CERN, near Geneva, Switzerland, is the world's largest and most powerful particle gas pedal, designed to probe deeper into the mysteries of the universe, such as the properties of the Higgs boson, dark matter, and other fundamental questions about the nature of reality. Beyond basic science applications, particle gas pedals have practical applications in a variety of fields, including medicine, where they are used to treat cancer with radiation therapy and to produce isotopes for medical diagnostics, industry, for processing materials and creating semiconductors, and art and archaeology, for analyzing paintings and artifacts without damaging them. The development and operation of particle gas pedals is a feat of engineering and physics, combining advanced technologies in superconducting magnets, vacuum systems, and particle detection to explore the limits of human knowledge. These machines are not just tools for discovery, but catalysts for technological innovation, facilitating progress in many fields and contributing to society's technological infrastructure. Particle gas pedals have played an important role in furthering our understanding of fundamental aspects of the universe, and have led to many significant discoveries that have shaped modern physics. These machines, by accelerating particles to high speeds and facilitating their collisions, have allowed scientists to penetrate the deepest mysteries of the universe, revealing the existence of particles and forces that make up the fabric of everything around us. One of the most revolutionary discoveries made using particle gas pedals was the identification of the Higgs boson. In 2012, scientists at the CERN Large Hadron Collider, LHC, announced the discovery of a particle corresponding to the Higgs boson, often referred to as the God particle. This particle, predicted by the Standard Model of particle physics, is fundamental to understanding why other particles have mass. The discovery of the Higgs boson was a monumental event in particle physics, confirming a key pillar of the Standard Model and contributing to the awarding of the Nobel Prize in Physics to François Englert and Peter Higgs in 2013. Particle gas pedals also played a key role in confirming the existence of quarks, the building blocks of protons and neutrons. In the late 1960s and early 1970s, experiments conducted at Stanford's Linear Accelerator Center, SLAC, this is the first direct evidence for the existence of quarks, confirming the quark model proposed by physicists Murray Gell-Mann and George Zweig in the 1960s. It was a significant step forward in our understanding of the structure of matter, establishing quarks as fundamental constituents of matter. The gas pedals have also facilitated the study of antimatter, particles that are identical to matter particles but have the opposite charge. Experiments at CERN and other centers have allowed physicists to create, trap, and study antimatter particles such as antihydrogen. These studies are crucial for testing the fundamental symmetries of the universe and for understanding why the universe is composed mostly of matter, despite the fact that the Big Bang Theory predicts equal amounts of matter and antimatter. Particle gas pedals have also enabled the discovery of many subatomic particles, including WIs and Z bosons, which mediate the weak nuclear forces responsible for radioactive decay. The discovery of these particles in the 1980s at CERN provided crucial evidence for the electroweak theory, which unifies the electromagnetic and weak forces, and was one of the key advances in attempts to develop a unified theory of the fundamental forces. In addition to fundamental discoveries, particle gas pedals have contributed to the development of medical treatments, such as particle beam therapy for cancer, as well as the development of technologies such as the World Wide Web, originally created at CERN to facilitate the exchange of information between scientists. So how do these experiments in particle physics confirm theoretical predictions? The interaction between theory and experiment in particle physics involves several key steps. Theoretical physicists develop models based on mathematical principles to explain the properties and behavior of particles and the forces that govern their interactions. These models often make accurate predictions about the outcome of certain interactions or the existence of previously unobserved particles. To test these predictions, experimental physicists design and conduct experiments using particle gas pedals. These facilities accelerate particles to high energies and then collide them, creating conditions that allow the observation of phenomena not normally available. Detectors surrounding collision points capture and record the particles produced in these collisions, and sophisticated data analysis techniques are used to interpret the results. An important aspect of validating theoretical predictions is the ability to reproduce experimental results. In particle physics, this often means that several experiments, sometimes at different facilities around the world, must observe the same phenomena under the same conditions. This repetition of results adds credibility to the conclusions and helps confirm that they are not statistical anomalies or artifacts of the experimental setup. The Standard Model of particle physics is a theory that describes three of the four known fundamental forces in the universe: the electromagnetic, weak and strong nuclear forces, and categorizes all known elementary particles. The model is a cornerstone of modern physics and represents scientists' best understanding of how the fundamental constituents of the universe behave and interact. The model has been developed over several decades, starting in the mid-20th century, through the collaborative efforts of physicists around the world. At its core, the Standard Model builds on the foundations of quantum mechanics and special relativity theory, combining them into a unified framework known as quantum field theory. The model divides elementary particles into two main groups: fermions and bosons. Fermions are the building blocks of matter that can be divided into quarks and leptons, including particles such as electrons, and the quarks that make up protons and neutrons. Bosons are force-carrying particles that transmit fundamental forces. For example, photons carry the electromagnetic force, and gluons are responsible for the strong force. A significant success of the Standard Model was the prediction and subsequent discovery of the Higgs boson, a particle that gives mass to other particles via the Higgs mechanism. The discovery made at the Large Hadron Collider in 2012 filled a crucial gap in the model and has been hailed as one of the most significant advances in physics, confirming the existence of the Higgs field and its associated particle. Despite the successes, the Standard Model is not complete. The model does not include the fourth fundamental force, gravity, described by the general theory of relativity, nor does it account for dark matter and dark energy, which appear to make up the majority of the mass and energy of the universe. In addition, the model's inability to account for gravitational forces or predict the masses of elementary particles suggests that it is part of a more complete theory that has yet to be discovered. While the Standard Model of particle physics is an extremely successful theoretical framework, it also has its limitations, marking areas where our current understanding of the universe is incomplete. These limitations not only emphasize the limits of the model's applicability, but also point to new physics beyond what we currently know, guiding researchers in the search for a more complete theory of fundamental forces and particles. One of the most significant limitations of the Standard Model is its inability to account for gravity. Gravity, as described by Einstein's general theory of relativity, is the fundamental force that governs the structure and dynamics of the cosmos on the largest scales, from the orbits of planets to the evolution of galaxies and the universe itself. However, the Standard Model is based on quantum field theory, which naturally does not include gravity. This contradiction between large magnitude, general relativity theory, and small magnitude, quantum mechanical theories is still one of the most important problems in physics. Another limitation is the Standard Model's silence on the nature of dark matter and dark energy. Observations of the universe show that about 85% of its matter is dark matter, which does not emit, absorb, or reflect light, and is detectable only by gravity. Dark energy, which accounts for about 68% of the total energy content of the universe, is thought to be responsible for its accelerated expansion. However, the Standard Model does not predict the existence of dark matter particles. It also fails to explain the properties of dark energy. So much of the universe remains unexplained. The Standard Model also fails to explain the matter-antimatter asymmetry observed in the universe. According to this model, the Big Bang should have produced equal amounts of matter and antimatter, which should have annihilated each other, leaving behind a universe full of radiation. However, the observed universe is dominated by matter, indicating that processes not considered in the Standard Model should have given matter an advantage over antimatter. The Standard Model does not provide a satisfactory explanation for the mass of neutrinos. The model originally assumed that neutrinos had no mass, but experiments showed that they have a small mass. This discovery necessitated a revision of the model, and also opened new questions about the origin of neutrino masses and their role in the universe. The Standard Model is a collection of particles and forces without a unifying principle that can explain why this collection of particles and forces exists. The main goal of theoretical physics remains the search for a theory of everything that unifies all fundamental forces, including gravity, and provides a deeper understanding of the particles themselves.